me squared over L squared. Okay, that's at the bottom of page, near the bottom of page 8. So at this point, he took this equation, notice, 1 over, and he stuffed that into here, here and here. Okay, and he ended up with what's at the bottom of page 8, which is minus k squared e to the 4th m over 2hc. And I hope you will actually do this algebra. And we have 1 over Lu squared minus 1 over L squared equals 1 over lambda. Okay, where again, capital L is the angular momentum of the electron. It's not the radius, but it's the angular momentum of the electron. Okay, it's at this point that Bohr had the really huge insight to say that he predicts that the angular momentum is quantized. What's really quantized is the angular momentum, and he's going to say that the angular momentum is equal to some integer times h over 2 pi. And why does he pick that? He just does. And h bar, what we call h bar, is simply h over 2 pi. That's simply another constant. So n here is equal to either 1 or 2 or 3 or 4. N becomes a quantum number. It's what we call the quantum number. Okay. So the very first quantum number, and he was right, the very first quantum number that was discovered by Bohr, and it deals with angular momentum of the electron. Okay. So what he did is he took this equation and he said, well, let's plug it into here and plug it into here and see what we get. And when he did that and he plugged it in, what he got was what's in toward the kind of a third up from the page. You got 2 pi squared k squared e to the 4th, the mass of the electron, divided by h cubed times c. All that is one big constant times 1 over n u squared minus 1 over n L squared equals 1 over lambda. And lo and behold, this fit the picture perfectly, because this is r times 1 over n u squared minus 1 over n L squared equals 1 over lambda. And n u and n L become the quantum numbers of the quantum steps. That is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And this r here now is a constant. And he said, well, I bet it's equal to all of this mess. And he calculated it out, and sure enough, it is. So using this theory, he totally derived what this Rydberg constant was. It's all of this mess put together. No one would have had any idea it was, but it turns out he was exactly right. And if you plug in the numbers for what these constants are, you calculate precisely what the Rydberg constant is. So it was a great confirmation of the fundamental ideas that the Bohr is trying to do when he was able to calculate Rydberg's constant exactly. Well, on page, that's a real quick synopsis of how Bohr came up with his atomic, the model of the atom. On page 10, 11, and 12, we have questions 1, 2, 3, 4, 5. And question 1 deals with just, I want you to calculate this equation using the Rydberg formula, calculate some of the actual hydrogen spectra. And then, let's see, do the same thing for question 2. I'm sorry. On question 1, what I want you to do is to actually graph the Balmer hydrogen series. That's right. On question 2, what I want you to do is to take this, and on the y plot, you plot this. On the x-axis, you plot this to see what, now if this is true, these should make, remember this is kind of like y equals mx. So this is make a straight line where the slope here equals the Rydberg constant. Okay? So I want you to plot this data, and I give you the actual data, and I want you to plot it, and I give you some graph paper on page 11. Now on question 2, I want you to calculate some more wavelengths. And let's see, page 12. Okay, question 3, this is probably the one that's going to take you the longest, is basically just describe how the base, you don't have to go through the entire derivation like I did, but if you want to, that would be great, just to do it in your own words, or just describe the basic steps that Bohr went through to show that the atomic energy levels are quantized. And then question 4, again, Bohr showed that the electron angular momentum L is quantized. Okay, what I want you to do is to plug that back into the electron radius equation on page 8, and to show how if you quantize the angular momentum, that also implies that the electron orbit radius, r, is also quantized. So you can derive what that quantization formula is. And then plug that into total energy, and you can show how the total energy is also quantized. That's simply straight algebra. Okay, it should be. If you have any questions, you can call me. And finally, question 5 is to calculate the very first quantized radiuses, R1, R2, R3, and R4 for the hydrogen atom. Well, that's the end of this. It seems like it's a lengthy lab, but hopefully you'll be able to get through it without too much problem. So long.